sorry for the wait. So thank you, Emmanuele, for being here with us virtually. And Emmanuele Ravaioli was awarded his PhD in applied physics at the University of Twente in 2015 for the characterization and demonstration of click, a new quench protection method. He had worked on superconducting magnet quench protection, multiphysics modeling, and superconducting circuit design since 2009 at CERN and at the Lawrence Berkeley National Laboratory, where he joined as a Turing Fellow. He developed CLICK, coupling loss-induced system, from the concept of Professor Green, Kirby, and colleagues. He wrote LEDET, a computer program to perform quench protection simulations that has been used in more than 10 laboratories and universities. Together with Dr. Marcheski, also at MPNL, he invented the quench detection technique based on stray capacitance monitoring. He's currently owner of the STEAM project for simulating transient effects in accelerator superconducting magnets and contribute to the LSC and high luminosity LSC magnet performance evaluation, research and development on quench protection methods, and scientific software development. Thank you, Emmanuele. Please start.
Thank you, Giorgio, for the introduction, and many thanks for the invitation. It's a pleasure and an honor to be here virtually with you to talk about protection methods for superconducting magnets. I'm Emmanuele Ravaioli, an applied scientist at CERN. I'm Italian, and I enjoy cooking pizza. It typically takes me about 1 hour to cook 6 pizzas, and during this time, my electric oven will have delivered an amount of energy that is similar to what you can store in a full-scale accelerator magnet. Only the electric oven gives this power in 1 hour. But there are conditions where you need to dissipate the energy stored in the superconducting magnet in a fraction of a second. So this is, of course, a very different power and not something we are used to very often. What makes it more challenging is that the superconducting coil is made of a conductor that is actually not much larger than the power cable we have installed in our homes. So it is quite a challenge and something to which I dedicate part of my career. But let's take a step back. It is desirable for many applications to reach high magnetic fields. And broadly speaking, you can do that by looping a conductor and passing a current through it. And generally, we can say that if we do more turns with the conductor, and if we put a higher current through the conductor, we will reach higher field. In accelerator magnets, typically we want to pack many turns and carry high current in a small volume, because a compact magnet is very important in the realm of accelerator magnets. So this forces us to work with very high current densities. And to give you the scale of how high the current density is in superconducting cables, consider that electrical appliances work with a conductor that carries a few tens of ampere. And superconducting cables have approximately the same size, but carry tens of kiloampere. So we are talking about current densities 2 orders of magnitude higher than what we're used to at home. And luckily, superconductors exist. Superconducting coils can carry electrical current without loss. And this makes it possible for them to operate at very high current density. They will remain in the superconducting state as long as temperature, magnetic field, and the current density will stay below a critical surface that is different for each superconducting material. During operation of a superconducting magnet, it's possible that an event called quench occurs. When this happens, locally, the superconductivity is quenched. This means that a small spot becomes resistive and is not superconducting anymore. The normal zone will propagate in 3 dimensions, and this is typically quite a violent event that includes several things all happening at the same time in a short time, period of time. You can reach high temperature because locally you will start having heating of a small spot in the coil. High voltages because you will locally start building up a resistive voltage across the coil resistance that is not superconducting, while the rest of the coil remains purely inductive. High stresses because locally you can have thermal expansion due to the heating of the conductor. If the magnet is cooled by a cryogen, you will also have a high pressure in the vessel. And during magnet design, typically it's not possible to exclude by principle that a quench can occur. And so you need to deal with the fact that at some points this may happen, which brings us back to the example of the oven. So imagine this is a device that is made to heat up stuff. We use it for 1 hour, and all the energy it delivered during this hour now is deposited in a tiny wire. Seems very difficult to avoid damage. But before I was born, the community already worked on that, and the main strategies that they came up with is extracting energy, so that the energy left in the superconducting coil is less, and the consequences of overheating are less severe. The second strategy is spreading the energy stored in the magnet over a larger volume of conductor. So this means that we will not deposit all stored energy in a tiny wire, but in a much larger volume. It's actually possible to design magnets to be self-protected. This is possible because as the coil becomes more and more resistive, an electrical resistance builds inside it. And this can be enough to discharge the magnet current quickly and keep the peak temperature in the coil low. I prepared an animation that shows this process in a superconducting magnet, choosing as an example a self-protected magnet installed in the LHC. On the right side of the slide, you see the temperature evolution in the magnet coil over time. You have a hotspot where quench starts, and a resistive zone that propagates longitudinally along the direction of the conductor and transversely due to thermal diffusion across insulation layers. As the time passes, and you see the time scale is milliseconds, so it's a very fast process, more and more terms are brought to the resistive state. On the left side, we can see in green the resistive voltage built up in the coil. And this is sufficient to discharge the magnet current in quite a short time. We are talking about hundreds of milliseconds. Lower current means lower heating of the hotspot, and the peak temperature in the coil can remain within acceptable limits. At the end of the transient, most terms are quenched, even those far away from the initial hotspot. Those that are far away were quenched due to eddy currents, not thermal diffusion. As the size and the energy density of the superconducting magnet increases, it is more and more challenging to make them self-protecting. One strategy to keep them self-protected is installing bypass elements across some coil sections. They could be resistors or diodes. So what happens is that effectively we split the problem into a smaller, more manageable problem. If a quench occurs in this red coil section and the green one remains superconducting, one can discharge the current of the red quenched coil section more quickly than the others because of the presence of the bypass element. On the other hand, the other coil sections, green, that are not quenched, can be discharged more slowly, but this is not a problem because they are superconducting. There is no heating there. Another technique that can be applied is coupled secondary elements that are metallic and in closer mutual coupling, magnetic coupling with the magnet coil. Professor Dean worked on this concept, and in this example that is taken from his work from the 70s, he showed that it's possible to transfer magnetic flux from the primary, that is the magnet to protect, to a secondary, that in this case is a bore tube in the cross-section of the magnet. I showed how you can passively spread energy in the coil volume in self-protected magnets, how you can passively extract energy using either bypass elements or coupled secondary elements. But as the energy density in the magnet to be designed increases, it is progressively more difficult or impractical to design self-protected magnets that use passive systems. In this case, active systems are needed to either extract the energy stored in the magnet or actively spread the energy over a larger volume. This is done by uniformly heating the entire coil volume. It is counterintuitive because in order to avoid overheating of a small spot with the severe consequences, we are heating on purpose the rest of the coil. It's counterintuitive, but it works. In the case of an active system, the first thing you need is a quench detection system that monitors the magnet and detects when a quench has occurred. There are a number of techniques available. The most broadly used is based on monitoring voltage across the coil for some coil sections. There is quite a number of alternative techniques that are in the R&D stage based on optical, acoustic, capacitive, or RF phenomena. I will not speak any more about quench detection in this talk today, but for the colleagues who are interested, I highly recommend the publication by Maxime Marchevsky, because it's a great read and gives a broad overview of these techniques. I will now present 4 active protection systems, 3 of which are conventional, and one called ESC is a new technique that I developed last year. The first system to present is the energy extraction system. The idea is rather simple. We introduce in the magnet circuit an energy extraction unit that includes a switch. This switch is open in case of quench detection, so that the magnet current is forced to pass through the resistor, and the magnet stored energy is discharged roughly exponentially. This is a straightforward system to design and implement, and also rather easy to simulate. The disadvantages of using this method is that typically the extraction unit can become larger and expensive, especially if you want to make it highly redundant. And the other issue with this method is that it does not scale very well with the magnet length. So if you have a high inductance magnet and high current density magnets, it becomes more and more challenging to protect a magnet with energy extraction and practical voltages. More crucially, in the world of circular accelerators, the most challenging magnets to protect usually are the bending dipoles that are typically installed in a series with many tens of magnets in series. If you apply energy extraction to such a circuit, the voltage across the energy extraction is subdivided over many magnets, and this makes it really not effective enough. The most active protection system that uses heating are the quench protection heaters. They are strips of stainless steel that are glued to the coil to protect. Upon quench detection, the strips are heated by driving a current through them. The heat is then transferred to the coil via thermal diffusion across a thin insulation layer that separates the strips to the superconducting coil. The local temperature increase is sufficient to turn parts of the coil from superconducting to resistive. And this allows the effectively discharge a part of all the energy stored in the magnet internally in its volume, but not just in a small spot, but more homogeneously over a larger volume. So the hotspot temperature can be effectively reduced. This is a well-known and established technology and is used in all high-field magnets installed in LHC, for example. Also, it scales well with the magnet length. If you have a longer version of the magnet, you can protect it with longer quenchitors with a similar performance. On the other hand, it is challenging to quench very quickly high-field magnets because you cannot make the insulation between the protection coil, the protection heaters and the coil protector too thin. Otherwise, you would put the electrical integrity of the heater at risk. So you are left with a practical insulation thickness that cannot be below a certain value, and this limits the top performance effectiveness of the heaters. Another challenge is that it's difficult or impractical to cover all the turns of the magnet and the entire length of the coil using heaters. In this animation, you see a typical transient of a magnet protected by heaters. On the right, you have a cross-section of the magnet where each rectangle is a different turn. And you have here the temperature evolution in the different turns. The heaters are put on the outside of the coil. So the first parts of the magnet that heat up are the ones in the outer layer of this magnet. On the top left, you can see the simulated current over time that is discharged purely because of the internal resistance developed in the coil. And on the bottom left, you can see the voltage to ground distribution along the conductor. This as a sort of repetitive pattern that is imposed by the sequence of resistive and inductive coil sections along the conductor. Another active heating system to protect the superconducting magnets is CLIP, the coupling loss induced quench system. CLIP relies on a capacitive bank installed directly to the magnet to protect it. During normal operation, this additional branch doesn't carry any current, but upon quench detection, the capacitor is discharged, and this introduces current changes with the opposite polarities in the two halves of the magnet. This locally causes very high field change, which in turn causes transient losses. These are special types of eddy currents that you have in superconductors. This turns out to be a very effective and fast mechanism to heat up the superconductor because it's heat deposited directly inside the conductor. This is largely sufficient to increase the temperature in most of the coil. So the coil turns resistive and the magnet energy is distributed more uniformly in the coil volume, again, reducing the output temperature. Together with the fast and effective heat mechanism, CLIP has also the advantage of relying on an electrically robust elements because it mainly relies on a lead that is connected or two that are connected to the coils to protect. The disadvantages include the fact that you need to directly connect the protection unit to the magnet circuit. And this can be cumbersome in the case of a circuit containing tens of magnets as a future circular command. Another challenge is to make the system redundant because you cannot simply install units in parallel since an electrical short circuit across one of them would short them all at the same time. The first idea to discharge a capacitor in a superconducting coil to protect it was proposed by Professor Green at Berkeley lab in the 70s. And Glenn Kirby, Vladimir Dashkov, and myself picked on the idea a few decades later and studied the concept, improved some of its parts, and characterized it and tested it on different magnets. Click is now a mature technology that in a few years will be installed to help protecting the inner triplet magnets of the foreseen for the high luminosity upgrade of LHC in combination with the ethers. Click relies mostly on one mechanism, at least in low temperature superconductors, and this is interfilament coupling loss. What you see on the screen is the cross-section of a superconducting wire that contains the superconducting filaments that have a diameter of micrometers or tens of micrometer and are embedded in a copper matrix. The filaments are twisted along the direction of the conductor. So when you apply an oscillating field transverse to the cross-section to the direction of the current, the change in magnetic flux seen by the loops formed by the filaments will drive currents between the filaments. These currents need to cross in the copper, and so they generate local heat. This is a pretty fast loss mechanism that typically has a time constant of milliseconds and has a power density that is roughly proportional to the square of the applied magnetic field change. In this animation, you see the transient of a typical transient of a magnet protected by click. On the left, you see the simulated currents over time. The blue current is the current discharged by the click unit. This imposes opposite current changes in the magnet current that are red and green. This is a working principle of click. So you are forcing the magnet current to have opposite polarities in some parts. You can see that the voltage to ground in the bottom left oscillates as well quite wildly when you discharge the click unit. And the desired effect you see on the right, where the hotspot temperature now reaches a value that is about 100 Kelvin lower than when using heaters. And also the temperature distribution is more homogeneous than before. As we push as a community for higher and higher fields in accelerator magnets, the requirements on the quench protection becomes heavier and heavier. LHC is based on main bending dipoles made of niobium titanium that are challenging but offer quite some margin in terms of peak temperature, peak voltages to ground, and peak stresses. Typically, quenching about 20% of the coil volume with an active system is sufficient to safely protect the magnet. For the upgrade to high luminosity LHC, niobium-13 quadruple magnets will be installed in the triplet circuits, and this will require tighter margin in terms of peak temperature and voltages to ground. As I mentioned, a new protection system was introduced to help protecting these magnets. But if we now target 14 to 16 Tesla magnets, the margins becomes even tighter, and a typical target for quench protection is to quench the entire coil volume in 5 milliseconds or less. This is quite difficult. For 20 Tesla and higher magnets, high temperature superconductors are needed. These superconductors are under R&D now and offer many opportunities, but will likely require dedicated and novel quench detection and quench protection methods, or progress on the techniques that are under the R&D now. So the challenges that I see in future quench protection is to achieve a very fast quench initiation, as you can with the click system, but without electrically connecting to the magnet circuit like the click method requires by principle. And also without relying on thermal diffusion, so that asks you to be in physical contact with the coil, like protection heaters do. It would also be nice if you were able to extract part of the magnet energy, like an energy extraction does, but without imposing a high voltage across the coil. And ESC, the energy shift with coupling, helps with these challenges, as I will show in the last part of the presentation. But before giving you the details on this method, I want to discuss 5 ideas that inspired the development of this new method. First, the idea of inducing a quench using inductive heating stations. Bromberg and colleagues worked on this technique in the 2000s and 2010s. And this involves small coils that are strategically placed close to the coil to protect, to provide an AC magnetic field and effectively quench the coil. During my PhD thesis, I also looked at some similar system, but relying on a single coil insulated from the magnet and coupled to the magnet to protect. And more recently, Tim Mulder at CERN is developing e-click, the external coil click system. This aims at quenching the magnet coil using thin, flexible, and easy to integrate small coils that you see on the screen. Another important idea, as I mentioned before, is a coupled secondary used to extract energy from the magnet during the quench process. And here I show on the screen again the work by Professor Green from the 70s. What I didn't mention before is that the schematic on the left contains an energy extraction. So this is an effective method, but in this embodiment, it shows an energy extraction. So for the reasons I explained before, this would not be easily applicable to a circuit with many magnets in series. But the coupled secondary is a good idea. And Matthias Menting at CERN built on this and proposed to design and integrate in the cross-section of a magnet absorption coils, so resistive coils that are sitting in the cross-section and not powered during the magnet operation, but during the fast quench transients, they can help absorbing part of the energy. And it showed that this idea could work nicely even for large magnets. I already mentioned the efforts by Professor Green and colleagues at CERN, and me included, on ways to use transient loss to our advantage to quench the magnet and protect the magnet coils. We showed that this technique can work on a wide array of magnet geometries and superconductor types. Matthias Menting, again, had also another good idea that he called the secondary click. This idea involves coils that have the dual purpose of quenching the coil and also extracting part of the energy stored in the magnet. So while I was simulating this technique and seeing how it was applied, applicable to high-field magnets, I actually came up with another concept called ESC, the energy shift with coupling. ESC can turn the magnet coil resistive and also extract part of its energy by shifting its internal stored energy. It forces high current change in the magnet current, but without putting high voltage across the magnet. In this sketch, you see a rest coil. So the green are the magnet coils, and you can imagine to add to the magnet cross section auxiliary coils, which in this case are placed on the top and bottom of the coils to protect. These coils are resistive. You can imagine them made of copper, well electrically insulated. You could have a millimeter or more of insulation and the method would work just the same. And strongly magnetically coupled to the magnet to protect it. And this is key for the method to work. Here you see a simple schematic of a superconducting magnet in green, together with an auxiliary coil in red. The schematic is pretty simple. It's just a closed loop because these auxiliary coils are closed on themselves, and during normal operation they are not activated, and there is no current through them, so they don't affect the magnet. But when a quench is detected, the capacitive unit that is connected to the auxiliary coil is discharged. This causes a fast rise of the current on the auxiliary coils, which in turn brings down the current in the magnet because of magnetic coupling. You can also imagine to install more than one auxiliary coil and power it independently. And in this case, this can help with the redundancy, will provide additional redundancy. And in general, the more coils you add that are well coupled with the magnet, the faster the discharge of the magnet current will be. ESC is based on 3 different mechanisms. The first is an immediate reduction of the magnet current that reduces the ohmic loss in the hotspot. The second is introducing a very high magnetic field change, and in this it does what click system does. This is to transfer most of the turns to the normal state quickly. Third, it extracts part of the magnet energy and deposits this in the auxiliary coils that are resistive. The final goal, as before, is to keep the hotspot temperature and the voltage to ground as low as possible. Here you see a simulation of a typical ESC transient, where you distinguish the 3 mechanisms I just described. When a quench is detected, we push a pulse of current in the ESC coils. Their current rises. At the same time, the magnet current is forced to drop due to magnetic coupling. And this sudden reduction of the current translates in a sudden reduction of the ohmic loss in the hotspot, because the ohmic loss is proportional to the square of the current flowing in the magnet coil. Simultaneously, this fast current discharge quenches most of the coil in a short time. And in the second part of the transient, let's say 50 milliseconds after the triggering and onward, the negative current discharge in the magnet pushes again a positive current change in the coupled coils, and this helps extracting the energy from the magnet that has quenched. So it seems ESC ticks all the boxes. It achieves a very fast quench initiation, but without having electrical contact to the coil, nor physically requiring physical contact to the coil to protect. And also extracts part of the energy, but does not put a high voltage across the coil. And since this mechanism is not very intuitive, I would like to go through the 3 mechanisms once again. So the key point for this not to be unphysical is that we are not dissipating any energy when we discharging the unit. The current in the magnet is very quickly discharged, but the stored magnetic energy in the system is only shifted temporarily to the mutual coupling energy between the magnet and auxiliary coils. So it does not require much power to shift the energy from the magnet coil to the auxiliary coils that are in close proximity. We do require high power to force a high region of the magnet coil to turn resistive. But we don't need the very large capacity units with large stored energy to do this, because the high power is kept only for a short time. And third, the energy transfer. So this works very well because there are no oscillations in the system. So everything just works to try to bring the current of the magnet down as quickly as possible. The voltage of the units is chosen to bring the current down. The resistance built up in the magnet coil brings the same. It brings down the current and up the current in the auxiliary coils that helps extracting even more energy. In this animation, you see an example of ESC transient. On the top left, you see in green the current flowing through the ESC coil. So the first bump is what is induced by the ESC unit, and the second shallower bump is due to energy extraction from the magnet. The red current is the current in the magnet, and you can see in correspondence of the activation of the ESC unit, the magnet current has a sudden drop. And on the right, you see that at this point, most of the turns are turned resistive and they start heat up. And at the end of the discharge, most of the turns have really very similar temperature, which is really difficult to do in a magnet, where some turns start the transit at 12 Tesla and some have almost zero field, because their magnetic resistance is quite different, and so they want to heat up non-homogeneously. At CERN, we are aiming at demonstrating the ESC technology on 2 magnets this year. One magnet is designed at CERN, and one magnet is designed at PSI. And I want to take the opportunity to thank the PSI colleagues, in particular Douglas Araujo, who include that technology in their subscale program. The roadmap for this demonstration starts with a conceptual design of the ESC system, selecting the conductor and performing the magnetic and mechanical design of the coils, as well as an integration study. This is because the ESC coils needs to be really installed in the magnets that are still being designed. The ESC coils are manufactured and assembled in the magnet before they can be tested. In parallel, I am also looking at how to apply this idea to a number of different magnets designed at CERN, PSI, or within the US Magnet Development Program. And I want to take the opportunity to invite any colleagues who have a superconducting magnet they are designing and are interested to try this new protection technique to reach out, because it would be exciting and so it's very interesting to try to apply to different magnet geometries or other applications. On this slide, you see pictures of the first 2 ESC coils manufactured at CERN on the left and at PSI on the right. These are meant to protect different magnets, so of course they are different in design, they have different conductor, but both of them are copper coils made with a single wire. The coil on the left is a racetrack coil with a G11 former, and the coil on the right is a common coil meant to protect a common coil magnet with a stainless steel former. Designing future high-field magnets with ESC in mind can allow for more robust designs, because the quench protection elements don't rely on physical contact with the magnet coils, so you can put very large insulation in your system, and the system will work just the same. The fact that you don't have direct connection to the coil makes it easier to integrate, and also opens the opportunity to make the system redundant, adding units with that are not in the main circuit, and you can add as many as you fit in the cross section. And the magnet will be safer to operate because you can aim for lower output temperature and voltages to ground. More ambitiously, you could think to even reach more efficient magnetic designs by making the cross-section more compact, since you need less copper to distribute the magnet stored energy. This is the case because you can extract part of the energy into the ESC coils. To design coils with ESC in mind, you need to reserve space in the cross-section for the auxiliary coils. So, of course, space is needed, and this will make the magnetic design less efficient because you have to use some space for something that is not generating a field during normal operation, and you need to think how to integrate the coil. Likely, you will need more than one ESC coil because each ESC coil will be very effective in quenching the thirst that it has close by. So you want to put a few in the cross-section to generate high loss in many terms at the same time. Mechanical analysis of the transient is required to verify that the forces acting on the ESC coils are sustained by the structure around. And finally, superconducting magnets are complex systems, so you need to have a careful study to see that you are not interacting with other systems. For example, you are not inducing eddy currents in metallic components that are part of the magnet to unwanted degree, or you don't have effects on the quench detection during ramps. Dreaming ahead, one can imagine that this idea could even open the space for designing accelerator magnets with higher current density in the copper than we are used to. Conventionally, the superconductor that is used in accelerator magnets contains superconducting filaments, but also copper. And this is for superconductor stability, for mechanical strength, but also for quench protection. Now, applying ESC to the magnet design can effectively extract 20–80% of the magnet energy. And this opens the door to work with very high current density, even in the copper. So the design would make more space for the current to flow in the superconductor and make magnets even more compact. To summarize, I showed why magnet quench protection is challenging and some conventional methods to protect them. I showed how the evolving magnetic field and the push for ion field asks for more effective protection systems, and I proposed ESC as a promising system to achieve this. The system should be demonstrated already this year. And I conclude my talk by mentioning that all the simulations that I showed today were performed using the STEAM framework. That is a project developed at CERN that I lead together with Mariusz Wozniak. We developed tools to simulate transits in superconducting magnets and circuits. And if you are interested in using the tools or you have some interesting cases to simulate, don't be shy and don't hesitate to contact us. Thank you for your attention, and I look forward to your questions.
Thank you, Emmanuele. Very nice. So I see there are some questions, but I have one. So let's start. I was wondering, what is exactly the design space where ESC starts to be required? And if you were to design, I don't know, current technology magnets, high luminosity, would they be better off with the ESC with respect to what is?
So I heard well the first part of your question and not very well the second part.
So the question is basically what is the optimal space of usage for ESC, basically when it becomes necessary, and what will happen if you use it in current technology magnets like Illumi, if they would be better off?
Thank you. So I would summarize it like this. I had this slide from another talk. For the magnets that can already be protected by an active system like protection ethers or clippers, you can very likely achieve the same performance of these systems, but with a more robust system. If you are still in the design phase, you can make the coil more compact because you will have a bit more margin. For magnets that are protected by energy extraction, it means that usually that they have a size and the current density that allows them to be protectable with this system. Still, you could apply ESC because if you allow us, when you apply the voltage, you are applying it to the external coils and not to the magnet itself. So you can get a similar performance of the energy extraction system, but using ESC. The price to pay in the design is that if you want to extract as much energy as an energy extraction system, likely you will have to integrate an ESC coil of a considerable volume. For the magnets that now we struggle to protect with all the systems that we know, this enables making these magnets and imagine to protect a full version, a full-length version of these magnets. I'm thinking insulated HTS coils for which, yeah, we have a solution that I think might work, but it definitely is a very big challenge.
Okay, so we have a question written in the chat. I think Jose Luis said raising his hand before. Do you, Jose Luis, want to go?
Sure. Hi, Emmanuele. Really nice talk. Thank you very much. I have a question about what are the plans for testing the system? You mentioned that you have your own coil that you built with Juan Carlos, and also you have the BSI coil, the subscale, right, of common coil that you're about to test. Is this happening very soon, or?
So we hope to be able to test on the coil built at CERN already this summer, because the S coils are ready. We are waiting for some parts, but for that we need 2 coils, and they need the G11 plate, and the mechanical design is already done. For the magnet design at PSI, we will need the 6 S coils, and we are not sure if we are going to use metal formers or not, and we are waiting for the mechanical study results to see that. But still, we think it's doable to do the test in the last trimester of 2024.
Okay. And then I have a second question about the point that you mentioned, that by having the ability to extract energy in this fashion, you would be able to make a lower copper and make the conductor smaller and make everything more compact. Do you have an initial study that let you know how much you can reduce the size of the coils using this technique?
Yeah, that's a very good question. The answer is no. I don't have it ready at hand. For the magnets that are still under the design phase, it is a challenge to work on the design and optimize the quench protection and also optimize S protection, because since it's R&D techniques, it cannot be the baseline. And so we are trying to do everything at the same time, but it's not easy. I think the magnets mentioned on the screen, so the 14 Tesla stress managed asymmetric common coil designed by Douglas in TSI, and the 20 Tesla dipoles designed by the US Magnet Development Program are a good test bed. Because these magnets are challenging. We want to have solutions that work. at the collaboration meeting of MVP, maybe you remember that I showed one case where ESC was more effective than the alternatives for one design of 20 Tesla, but this is not a very broad study yet.
Okay, thank you very much.
So there is a question in chat. Mary Roberts is asking, is there work to reduce or even prevent the quenches? The cause. In the case of NMR magnets, they epoxied all layers to avoid movement during energization, and the ramping was also controlled. Maybe you can read it. Can you say something about it?
So that's always the best to avoid. So for low temperature superconductors, this seems, I would say, I never like to say impossible, but it seems impossible to avoid by design, because the quantity of energy needed to start a quench is really minimal. So you would need to avoid many events that could happen. On top of that, yes, it's true, and there are very nice efforts in the community to reduce quenches with different design concepts or different impregnation methods used. But there are still things that can happen in the life of a magnet. Some loss of cryogenic fluid, some manual mistake by an operator. If they are installed in a machine, you could have beam losses that cause quite significant losses. So to really prevent quench completely during the life of the magnet is really tricky. Preventing training is a very interesting engineering challenge. This might be possible, but to prevent that anything that will happen in the life of the magnet will not have a quench is really very good. Now, for high temperature superconductor, it's true that you might get very early warning that a thermal runaway is about to occur, and you might have you might stay for a really long time in a regime where you know something is off and you have time to power down the magnet. But still, really, I work on quench protection every day, so it's difficult for me to accept that by design you can completely exclude that whatever will happen in the operation of these magnets will not cause a quench. Another example is magnets that are an inset and outset. I know this is not a very common case, but if two magnets are physically close and are magnetically coupled, if one quenches, the other can quench.
Are there any other questions from the audience? Okay, so can I ask you, how does this apply to HTS magnets, and any plans of trying on one, this concept?
Yeah, I think this is very interesting. So for BISCO 2212 HTS, we have the tools to simulate a radial fender. So you know that this superconductor comes in round filaments, and it can be made on routed for cable that are similar to titanium and non-tritium cables. So in this case, the tools that we have to simulate low temperature superconductors can be immediately used for these cases. And in this case, I would say we are ready to look at this case. Magnets that are made of Repco instead have first a challenge that there are multiple types of cables that are made of Repco. So you have typically, I mean, they come as tapes, but then you can have rubber cables. You can twist, you can stack and twist them. You can have cord conductor stuff. So each of them likely requires, I want to say, a PhD thesis amount to understand well transient loss of all types that can occur. And then when we have that, we can implement it in simulation tools. We are working on this, not with the PhD study, but there are colleagues in the team as a postdocs that are working on these topics. Julian Morar in particular is Goulart in particular is on this, and let's see. I would say once the technology is demonstrated on low temperature superconductors, maybe we will also have the momentum to propose to try it on HTS forms.
Okay, perfect. I think we don't have any more time. So thanks again, Emmanuele. It was nice to talk. And bye, everybody.
Thank you for the invitation and for the attention.